All right, so in this third of our five-part video series on trade wind inversions, we now want to dig into a mathematical framework which allows us to quantify inversion strength as well as to some extent altitude. This is going to come through what is known as the lapse rate tendency equation. So let's start by taking a step back to what we saw in our previous video here, where we had a sounding from Vandenberg Air Force Base in California uh, in terms of the temperature trace given by the black line that we see through here. We have the height at any given level with the number on the left, and we have the mixing ratio value given by the number on the right in grams per kilogram. Before, we looked at how the trade wind inversion, this inversion layer here in the middle between about 960 and 810 hectopascals, separates the marine influenced atmospheric boundary layer, or just the marine layer, from the free troposphere, the free atmosphere that resides above. Now we want to understand the properties of this inversion layer. So we know that by definition, temperature changes are inverted across an inversion. Temperature typically decreases as you go upward with height, and yet across an inversion, they typically increase, or at worst, they stay the same across that inversion layer. So it's the inverse of what we typically would expect to see. We see this in terms of our temperature. The bottom here is about 12 degrees Celsius if we read off relative to the isotherms that slope from bottom left to upper right. And the top part of our inversion hugs right along that 20 degrees Celsius isotherm. So in this case, the temperature increased by 8 Celsius across the inversion. But we can also look at this not just in terms of temperature, but in terms of potential temperature. So we can read off our potential temperature values by going down parallel to the dry adiabats until we reach 1000 hectopascals. Can do that for the bottom of the inversion layer and for the top of the inversion layer. And in this case, it's nice that these dry adiabats actually have the potential temperature values labeled on them here. You can see that 283 and the 10 cross right there at 1000 hectopascals. 10 Celsius temperature, 283 Kelvin potential temperature, which is exactly what we would expect. 10 Celsius plus 273 gets us to 283 Kelvin. And so here at the bottom, we're roughly halfway between the 283 and the 293 Kelvin lines, maybe a little bit closer to the 293 line. Whereas here at the top, we're pretty close to that 313 Kelvin line. So if we throw up what those potential temperature values are ultimately would be, we see that the bottom's about 288 Kelvin and the top is about 310 Kelvin. We had an 8 Celsius increase in temperature across the inversion, but because that temperature line cuts across the dry adiabats at a very steep slope, we actually get an even larger increase in potential temperature over this layer. From 288 to 310 Kelvin, that's 22 Kelvin change over the course of about a 1.5 kilometer deep inversion layer. So as a result, potential temperature increases rapidly with height. I know that's probably cut off a little bit by my video there, but the key point here is that as you go upward, potential temperature rapidly increases. It typically does increase with height, so long as you don't have a temperature trace that parallels a dry adiabat or is super adiabatic. So it's not that it's positive with height, but that it's very, very much so positive with height that we're particularly interested in here with regards to the inversion. So if we look at above the inversion, we go from 310 and we get to 313. If we go up by that same 1.5 kilometers or so, we end up here where we're about halfway between 313 and 323. So we have about 8 Kelvin as compared to this 22 Kelvin change across the same thickness associated with the inversion. So we can define the lapse rate based off of either temperature or potential temperature. We typically think about it as the change of temperature with height. dt dz would equal our lapse rate. But we can also do this in terms of potential temperature with height. In this case, we'll utilize pressure as our vertical coordinate. So there are some very nice properties of applying this on pressure surfaces, namely that relationship between divergence and vertical motion that we've hinted at in our previous videos as well as earlier in the semester. And so we have the lapse rate gamma here on the left-hand side is equal to the negative of the change in potential temperature over the change in pressure. And so we know that through an inversion, potential temperature increases as you go upward. So this numerator should be positive. We know that pressure decreases as you go upward, so that denominator should be negative. Positive over a negative gives us a negative, but that leading negative gives us a positive. So through an inversion, this lapse rate should ultimately be positive, and in particular, it should be very much positive, which we indicate here through the double greater than signs, not just the single greater than sign that is our typical condition, but the double greater than signs to indicate that this is a big deal. This is a really big increase. So thus, strengthening the trade wind inversion, not just taking what is already there and diagnosing what is there, but if we look at how that is changing forward in time, a strengthening trade wind inversion is one in which this lapse rate gets even more positive, say from 22 Kelvin increase that we saw in our previous example to 25 Kelvin increase, or sorry, 25 Kelvin period. So you'd be looking at 25 as the later time minus 22 as the current time divided by that change in time, so you get a positive value there. And ultimately, that's what we're interested in. What is this lapse rate? We know that it's very strongly positive with the inversion. And how does it change in time? The partial derivative of this lapse rate with regards to time. And that's where this lapse rate tendency equation comes into play. The full derivation of this equation can be found in the trade wind inversion lecture notes that are posted both to Canvas as well as to the course's main website back on my personal website here. We start with the first law of thermodynamics and we do a whole bunch of manipulation. It's about a 2 or 3 page derivation within those lecture notes. And ultimately we get this lapse rate tendency equation that on the left-hand side is simply the change in the lapse rate over the change in time here. You get a whole bunch of nasty looking terms here on the right hand side, and it's the remainder of this video as well as the two that follow from this where we'll dig into just what all of these terms ultimately mean. You'll note that many of these terms, like our lapse rate here on the left, as well as many others here on the right-hand side, have overbars, these horizontal lines that we see here. These indicate large-scale averages, so looking at the synoptic scale over the eastern North Pacific, not just a specific location at a specific sounding, for instance, but broad scale in terms of our interpretation. We do have a couple of prime terms that show up here in terms of the second partial derivative, omega prime and theta prime, and these represent cloud scale departures. So we're looking at the large scale, and then here with those two prime terms, we're looking at individual clouds, and in particular, the motions that are found within those clouds. But you'll note that there's an overbar on top of those terms as well. So we're looking at the large scale average of all of the clouds that may be found within a given larger scale region. So we're not going to have to get down to the scale of an individual cloud and compute what's happening there and then go upscale. We'll take a much more analytical approach to this and look at what's happening for a generic cloud and assume that that is representative of the entirety of that larger scale environment here. So there ultimately are 6 forcing terms on the right-hand side, which I've labeled with A, B, C, D, E, F here on the bottom. This F term here actually has a summation as a function of some subscript of I here. And there's actually 5 different heating terms that comprise this H sub I, which H stands for diabatic heating here. So in actuality, we don't have 6 terms A through F, but we have 5 forcing terms A through E, plus 5 heating terms here in F, for a total of 10 different forcing terms to the lapse rate tendency equation, all of which is helping us get at just what the change in lapse rate associated with the inversion is with time as a function of each of the different physical processes here. Again, it's looking pretty nasty here. We've got some gradients, we've got some dot products, we've got some partial derivatives, we've got a second partial derivative here, and we've got a whole mess in our heating tendency equation. But that's the point of stepping through this relatively slowly. We're going to take a look at each one of these terms in some detail. So in the remainder of this first lecture, we're just going to very briefly introduce each of those 6 forcing terms. It's in the subsequent 2 videos where we'll actually dig into each of those terms. We'll take the first 4 in our next video, and then the last 2 in our final video in the series here. So this first term, this partial derivative of V with respect to P dotted into the gradient of the potential temperature field, we call this the differential horizontal potential temperature advection. So this term kind of looks like an advection term. We've got a gradient operator here with a dot product in front of it. And so advection usually looks like the wind dotted into the gradient of some scalar quantity that we see here. In this case, we're not looking at the wind dotted into the gradient, but the vertical wind shear associated with the dot product into the gradient here. So that's how this term gets its name differential. It's representing advection by the derivative, and in particular the vertical derivative of the wind, which is really just the vertical wind shear, the change in wind over the change in pressure, which is related to the change in height here. And so differential is this change in wind, horizontal potential temperature advection is that advecting the horizontal potential temperature field that we see here. Fortunately, this term will be one that we can ultimately end up neglecting for reasons that we'll describe in a little bit more detail in our next video. If we go to the second term, now this one's a lot more familiar to us. We have the velocity dotted into the gradient of the lapse rate here. And this is simply a horizontal lapse rate advection term. Again, negative of the velocity dotted into the gradient of the lapse rate here. We can infer the sign and the magnitude of this term from the climatology that we took a look at before. We know where the inversion is strongest. In particular, we saw that it's strongest close to the coast of North America, and that's going to lead to the most positive of lapse rate being found there as well, for reasons that we'll dig into in our next video. We also know where the wind is and how it's directed away from that coast toward the central Pacific Ocean. So we'll be able to use those 2 diagrams to help us interpret just what this term is analytically and physically doing to the lapse rate. We also have a vertical lapse rate advection term. It may not look like it necessarily because we don't see a dot product into a gradient, but we know that the vertical component of the velocity is omega, and we know that the vertical component of the gradient is the partial derivative with respect to pressure here on an isobaric surface. So really, if we just took the advection term on the previous slide and had those vertical parts in them, this is ultimately what we would get out. The vertical velocity multiplied by the change of the lapse rate with respect to the change of pressure. And so we can also figure out just what this term would look like from the images that we have on our previous video. The vertical velocity we can relate to the strength of the low-level divergence. Again, we introduced this very early in the semester and we took a look at it a couple of videos ago in this sequence. If we know what the divergence profile looks like, we can infer what the sign of the vertical velocity should ultimately look like. We can infer how the inversion, or really the lapse rate more generally, changes in intensity with height from things like that vertical cross-section between San Francisco and Honolulu on either side. We know that as you go up through the inversion, the change in temperature changes, as well as does the change in potential temperature through that region. So we'll be able to look at that to help us interpret this term. We come to our fourth term now, the divergence term. And you might be saying, I don't really see divergence in here. I see the lapse rate and I see the change in vertical velocity with pressure, but where does divergence come in? It's in that second term, the change of the vertical velocity with pressure. Divergence itself, when we're dealing with this isobaric coordinate framework, constant pressure surfaces, divergence is just du dx plus dv dy, what we've been calling delta. That equals negative d omega dp on isobaric surfaces through the continuity equation. So really what this top term is the lapse rate times the divergence, and that's how it gets the name divergence term. So really, if we think about it in terms of how it appears here, it's the effects of vertical variations in vertical motion, change in vertical motion, change in pressure, change in height on the lapse rate. And because of that relationship for that quantity to the divergence, all we need to know is what the lapse rate is, really the intensity of the inversion, and the strength of the divergence, which we have from that low-level wind field. That allows us to be able to analytically evaluate this particular term. Things get a little bit more complicated as we get to our fifth term, which is this one that involves a second partial derivative with respect to pressure, two prime terms multiplied by each other with an overbar on top of all of those. We said that those primes refer to cloud scale processes. And here we're looking at vertical velocity here. So within clouds relates to the fact that these are occurring on the cloud scale. Vertical mixing relates to the fact that we're dealing with vertical velocity here, and it's mixing of potential temperature. Recall, potential temperature is what defines the lapse rate in this formulation. So if you're changing the potential temperature by up and downward motions within clouds, you're going to be able to change the lapse rate in the vicinity of that cloud. Here we're looking at the larger scale effects of clouds all within a broad region and looking at their aggregate impacts on the strength of the inversion. So really, if you wanted to try to look at this analytically, it's a pretty nasty looking term. The second partial derivative, we need some sort of finite difference approximation to work with this. And how do we handle these prime terms and the overbar? Yuck. Fortunately, when we look at this physically, it's not that bad, and we'll describe how that looks like in our subsequent video. We'll have to talk a little bit about what turbulent motions within clouds look like in the context of how potential temperature typically appears beneath, through, and above the inversion to be able to do that, but it ultimately is not too bad. So finally, we get to our fourth term, which is really, or sorry, our final term. I got mixed up with the F there, which really is not just one term, but is the combination of 5 terms. And this H that we see here refers to diabatic heating, but there are 5 different sets of physical processes that we're looking at in terms of diabatic heating. That's where this summation comes in. So this first term here on the left-hand side looks pretty gnarly. We have a partial derivative with pressure. We've got a bunch of variables here before we even get to the summation, and then we have h sub I that we're ultimately summing over. Fortunately, we can simplify a bit. Most of these variables that show up right before the summation, C sub P is a constant, P naught is a constant, R is a constant. And if we're looking at a single pressure surface, or really between pressure surfaces as we see here, pressure is a constant on each one of those pressure surfaces by definition. So all of these terms here are just positive valued constants for our consideration. So this symbol here means is proportional to. And so it really boils down to just the partial negative of the partial derivative with pressure of each one of the heating terms here. We have one related to convective precipitation, one related to non-convective precipitation, one related to evaporation within regions of precipitation and in particular not precipitation. We have surface sensible heating from the underlying ocean, and we have radiation that we see here. Fortunately, these first two that relate to convective and non-convective precipitation, we don't typically see precipitation, at least of that intensity, in association with the trade wind inversion. So we'll ultimately be able to neglect those two terms that we see here and here. But that still leaves us 3 terms to be able to unpack. We'll find that evaporation is partially related to clouds, radiation is also partially related to clouds, and surface sensible heating is related to, as you might guess, the surface. So we'll dig into that in a little bit more detail in our last video in the series. So summarizing here, inversions are characterized by that large increase in potential temperature over a short vertical distance, a positive lapse rate as we've defined it here. It's always positive unless you have a dry adiabatic or super adiabatic layer, but it's really, really, really positive through an inversion. A strengthening inversion means that something that is already really positive gets even more positive over the course of time. And we've introduced a mathematical framework here through this lapse rate tendency equation that allows us to introduce and identify the physical processes that influence inversion strength, but also where the inversion is found. And so in our next video, we'll start to dig into this by taking a look at the four simpler terms in terms of the lapse rate tendency equation before we dig into the more complex terms that involve clouds and diabatic heating in our final video in the series. Until then, thanks for tuning in.